Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear student, today we are going to discuss another technique for studying the surface information, grain size, grain positions, information, chemical makeup, and many things. For that purpose, we use scanning electron microscope. In short, it is called SEM. S for scanning, E for electron, and M for microscope. This is the much more versatile technique that is used for topographic study of organic and inorganic materials from nano to micro region scale. You know, every apparatus has its own limitation, or eye has its own limitation. It can resolve things up to certain limits, but when eye fails to resolve, we go for simple microscope. When simple microscope fails to resolve, then we go to optical microscope in which we use light. When optical microscope fails to resolve, then we go to the most modern techniques, scanning electron microscope. We will discuss how does it work and how can we view things with the help of the scanning electron microscope. So, scanning electron microscope is basically used to study very small object which we can't see, that is in micro region, micro or nano or milli size. We can visualize with the help of scanning electron microscope. The magnification of SEM, magnification in general, is the ratio between the size of the image to the size of object, varies from 10 times to 1000 times, meaning that 10x means 10 times, 100x means 1000 times, meaning that then object size can be enlarged from from 10 to 1000, meaning that object size is 1 millimeter, from 10 millimeter to 1000 multiplied by 10, from 1000 multiplied by 1 millimeter, 1000 millimeter, that can be viewed like that. So, the magnification of SEM varies from 10x, meaning that 10 times, to 1000 times multiply, and that will be magnified, and depends upon the electron speed. We will discuss it later. And magnification is from 10x to 1000x, and its resolution ranges from 1 to 5 nanometer, meaning that if the objects are very close, meaning that from 1 to 5 nanometer, if you want to see it with the scanning electron microscope, then you will see it separately, meaning that if the distance between 2 points or 2 particles is from 1 nanometer to 5 nanometer, then you can see them separately with the help of scanning electron microscope. The idea of scanning electron microscope was floated by H. Stezing in 1927, while the first image was developed by H. Knoll in 1935. Idea was generated by H. Stezing 1927, and that idea was taken and the image was developed by H. Knoll in 1935. ECM जो होता है क्या है, ECM is a modern technique for studying surface topography, compositional analysis, crystallographic information and grain size of the material with high magnification and high resolution. Surface topography means surface morphology. What type of surface does it have? How much size grain the material contains? Whether domain exists in that grain or not. Compositional analysis, how much is the ratio of the composition from which the compound is made up. For example, barium titanate, how much is the composition of barium, how much is the composition of titania, how much is the composition of oxygen, so that. And crystallographic information we can also get from it. Grain size of the material, that can be viewed with a clear that will be sighted clearly with the help of the scanning electron microscope. So, ECM can be used for structural study of material over a broad range from 10 to the power 2 to 10 to the power minus 2 micrometer. That can be used for structural study from 10 to the power 2 to 10 to the power minus 2 micrometer sizes. So, the highly accelerated electrons are focused. What is the operation of that one? The highly accelerated electrons are focused on the specimen. You might have remembered that de Broglie hypothesis. Each and every moving particle is associated with the wave nature. So, here electron are accelerated. The more they are accelerated, the lambda is equal to h by mv. Lambda is inversely proportional to the speed of electron. So, the more you speed up the electron, the smaller will be the wavelength. When the smaller is the wavelength, the more will be the resolution, because resolution and wavelength has the inverse function with each other. So, the highly accelerated electrons are focused on the specimen, which may scans across the raster, meaning that they are scanning on the specimen to produce the image. The highly energetic beam of electron interacts with the specimen, resulting in the backscattered electron, secondary electrons, OJ electron, characteristic X-rays and some other photons of various energies. When these high energy electrons strike the specimen, a lot of radiations are being emitted. One is backscattered electron, the same electron which is reflected elastically, and the other electron which is first absorbed in the specimen and then absorbed, that is called secondary electron, which is of vital interest. Then OJ electron, then characteristic X-rays and some photons of other energies that may be of visible, that may be of infra, that may be of ultra. So, these are the radiations that results from the impact of electron on the specimen. Now, these signals are generated from SAED, selected area electron diffraction of the specimen. Selected area meaning that the area you have chosen, you choose usually in electron microscopy. I will show you in a video. There is a specific area on which electrons are being that is being selected on electron microscopy. That is what we call selected area. Sometime we call energy dispersion कहते हैं, sometime we call electron diffraction कहते हैं. So, these signals are of the specimen and are used for surface analysis. So, crystallographic informations, compositional analysis and many more. Scattered and secondary electrons are of much interest in all generated signal, as these are generated from a result of different surface topography. the secondary electrons are responsible for image formation. Secondary electrons are collected. One is a big scattered electron. For that we have a separate detector. For secondary electron we have a separate detector. From big scattered electron we see the chemical composition, and from the secondary electrons image is being processed and generated by the computer on a computer screen. You will see it in the later part of this lecture. So, the secondary electrons are responsible for the image formation of the specimen. The characteristic X-rays generated from the sample gave both qualitative and quantitative elemental informations in 1 micrometer depth and diameter each. So, meaning that X-rays जो होते हैं वो आपको qualitative and quantitative elemental information देती हैं. How much is the quantity of the element in the compound. So, that is giving you that information. So, from that we see big scattered electron are basically used for the processing of the image for the surface topography. Secondary electron are being used for the surface topography. Big scattered electron give you elemental analysis also, and then we come to X-rays. X-rays give qualitative and quantitative elemental analysis, how much is the ratio of the element in the compound, and so on. So, large depth of field of ECM is responsible for 3-dimensional image of the specimen. So, 3-dimensional image of the specimen can be obtained with if the field has a large depth. So, the secondary electron based ECM was developed in New Jersey RCA laboratories during World War time. That was developed in the World War time. The first ECM image was images of the Otley and his colleagues were obtained in 1951 and was commercialized in 1958. So, that was about a little bit story about that one. Now, come to the principle which we a little bit quickly highlighted. Now, we are coming. The ECM is comprises of lens system, but that is not the optical lens. This is magnetic lens system, electron gun which is responsible for generating electron collector, that is when the electron are released by sample, they are being collected by a detector, that is called electron collector. Visual and recording cathode or cathode ray tube, meaning that positive charge is being given to the detector and electron are being attracted, so they are being collected by the detector. So, electrons generated by means of field emission or thermionic emission is accelerated towards the specimen by the application of voltage. Electron can be generated either by means of thermionic emission, meaning that if you heat a filament, electrons are by application of electric field, which is called electric field emission technique. So, the primary beam of electrons suffer 2 types of scatterings. प्राइमरी बीम ऑफ इलेक्ट्रॉन जो है वो 2 टाइप के स्कैटरिंग, एक तो है इलास्टिक एंड इनइलास्टिक स्कैटरिंग ऑन इंटरेक्शन विद द स्पेसिमन. One is elastic scattering and other is inelastic scattering. Elastic and inelastic, you are clear of it. When a certain thing falls on it, there is no change in energy and momentum, then it is called elastic collision. And inelastic collision, when kinetic energy is different than the initial one, linear momentum is conserved. So, this is inelastic collision. In inelastic scattering, the electron interact with the nucleus without losing energy, whereas in inelastic scattering, electron loses its energy either through Coulomb field by emitting continuous X-rays or ejecting secondary electron. या तो Coulomb force की वजह से deviate हो जाता है और थोड़ी सी energy क्या कर लेता है, लॉस करता है, या secondary electron को क्या कर लेता है, वो eject कर लेता है, निकाल लेता है from the specimen. These signals are collected by the detector and the image of the specimen is produced. The secondary electrons are being collected by a special type of detector and the image is being produced. You see this is a small image of what? This is the image of the processing technology. So here you see, this is here the this is the filament, the small one, this is the filament which is heated, electrons are being emitted and high voltage is applied over here to focus electron. These are my electromagnetic lenses. Electromagnetic lenses focuses the electron properly into the specimen where the electrons are roasting, are moving here and there, and the signal generated are here. That is secondary electron, X-rays, big scattered electron, cathode rays, cathode rays हैं, different type of photons है, और J electrons है. So these are being emitted and different radiations are playing different role in developing the image, in studying the chemical composition of the element. ये role जो है ये play करते हैं इसमें. So the magnification, resolution and depth of focus, देखो ये सारा मैंने क्विकली कर दिया बिकॉज आप थोड़ा सा गूगल कर लें, वो सब कुछ आपको ना. द मैग्निफिकेशन, रेजोल्यूशन एंड डेप्थ ऑफ फोकस ऑफ ECM मेनली डिपेंड्स अपॉन द वर्किंग डिस्टेंस, मीनिंग दैट सैम्पल और उसके दरमियान जो है बीम जो फोकसिंग वगैरह लेंसेज के दरमियान क्या होता है, फासला क्या होता है, विच इज़ द सेपरेशन बिटवीन द सैम्पल एंड द डिटेक्टर. डिटेक्टर और सैम्पल के दरमियान फासला कितना है, दैट इज़ कॉल्ड वर्किंग. डेप्थ ऑफ फोकस इज़ इंक्रीज्ड वेयर एज रेजोल्यूशन इज़ डिक्रीज. जब डेप्थ ऑफ फोकस को इंक्रीज़ करते हैं, डेप्थ ऑफ फोकस जब आपने रेजोल्यूशन को इंक्रीज़ करना होता है तो डेप्थ ऑफ फोकस इज़ इंक्रीज. डेप्थ ऑफ फोकस जो होता है यानी इलेक्ट्रॉन को फोकस करने का वो भी इंक्रीज़ होता है. एग्जामिनिंग कम्प्लेक्स सैम्पल एट लो मैग्निफिकेशन, जब आप लो मैग्निफिकेशन पे कम्प्लेक्स सैम्पल को क्या करते हैं, स्टडी कर लेते हैं. फॉर हाई रेजोल्यूशन अ मच स्मॉलर स्पेसिमन इज़ रिक्वायर्ड so that working distance can be minimized between the sample and the detector. sample और detector उनके दरमियान working distance को minimize करने के लिए हम क्या कर लेते हैं, हाई रेजोल्यूशन. जब भी आपको स्मॉलर चीज़ को देखना होता है तो आपकी रेजोल्यूशन हाई होनी चाहिए ताकि वो बिल्कुल अलग अलग और वाज़ेह नज़र आए. लार्ज साइजेस सैम्पल आर यूजुअली पोरस. लार्ज साइजेस जो सैम्पल होते हैं पोरस होते हैं एंड कैन पोल्यूट द वैक्यूम ऑफ द डिस्चार्ज ट्यूब, और उससे आपका जो है इमेज जो है वो एग्जैक्टली सही नहीं आता जिस तरह के आना चाहिए. मतलब ये हुआ कि जब भी आपने सैम्पल लेना है उसके लिए तो आपने कौन सा सैम्पल लेना है, कोशिश ये करो कि सैम्पल छोटा से छोटा हो ताकि उस सैम्पल के अंदर जो है ये पोरासिटी होती है, उसके अंदर गैस होता है. वो होता है जब इलेक्ट्रॉन आते हैं तो उससे वो गैस निकलेगा, जब निकलेगा तो वैक्यूम को पॉल्यूट करेगा, वैक्यूम को पॉल्यूट करेगा तो ये जो इलेक्ट्रॉन फिर आ रहे हैं वो रास्ते ही में एनर्जी को लॉस करेगा और आपका मकसद जो है पूरा नहीं होगा और आपका इमेज जो है वो क्या आएगा, ब्लर आएगा. तो इलेक्ट्रॉन माइक्रोस्कोप में आपने देखा एक होता है फिलामेंट. फिलामेंट का काम है क्या, ये इसको बेसिकली इलेक्ट्रॉन गन में आता है. ये फिलामेंट का काम है इलेक्ट्रॉन को एमिट करना, और ये इलेक्ट्रॉन जो एमिट होता है तो उसके लिए हाई एनोड लगाया होता है, हाई वोल्टेज एनोड लगाया होता है जिसको नीचे क्या करता है, एक्सेलरेट करता है. ये इलेक्ट्रॉन डिस्पर्स होता है और उसको इंटेंसिफाइड बीम बनाने के लिए, प्रॉपर फोकसिंग के लिए ऑप्टिकल लेंस की बजाय उसमें इलेक्ट्रोमैग्नेटिक लेंसेज लगाई जाती हैं. और ये इलेक्ट्रोमैग्नेटिक लेंसेज जो होती हैं इन द फॉर्म ऑफ काइल्स होती हैं और ये इलेक्ट्रॉन को क्या करती हैं, रोस्ट करती हैं, स्कैन करती हैं अक्रॉस द सैम्पल. और जब अक्रॉस द सैम्पल सेव करती है तो इसमें से जब इलेक्ट्रॉन पड़ जाता है तो एक इलेक्ट्रॉन बैक स्कैटर्ड हो जाता है, इलास्टिकली स्कैटर्ड हो जाते हैं, और दूसरा जो है कुछ एनर्जी लॉस करता है कूलम्बिक फोर्स की वजह से, या कुछ एनर्जी जो है वो क्या होती हैं, वो एब्जॉर्ब हो जाती हैं उसमें. और इसके अलावा ये जो है एक्सरेस को जनरेट करता है. इसके अलावा ओजे इलेक्ट्रॉन को वो एमिट करता है. एवरीवन हैज़ इट्स ओन रोल इन इट्स फंक्शन. एक्सरेस को हम केमिकल मेकअप, एलिमेंटल रेशूज़ के लिए वो क्या करते हैं, इस्तेमाल करते हैं, जबकि बैक स्कैटर्ड इलेक्ट्रॉन जो होते हैं वो इमेज प्रोसेसिंग के लिए इस्तेमाल होते हैं. इमेजेस आर बीइंग प्रोसेस्ड विद द हेल्प ऑफ द बैकस्कैटर्ड इलेक्ट्रॉन, और इस तरह हमें इंफॉर्मेशन मिल जाती है. नाउ आई एम गोइंग टू डिस्प्ले बिकॉज मैं जितना भी एक्सप्लेन करना चाहूँ तो बहुत ज़्यादा टाइम लेता है और आपको सही तौर पर से वो नहीं आएगा. लेकिन अगर मैं आपको एक छोटी सी वीडियो क्लिप बता दूँ तो यू विल सी एवरीथिंग व्हाट आई हैव डिस्क्राइब्ड इन माय लेक्चर. कम एंड सी.
The scanning electron microscope. Scanning electron microscopy is one of the most fascinating examination methods. This video shows how it works in practice. Main components of the microscope are column for electron beam generation, specimen chamber, vacuum pump, monitor, and control panels. The material tester turns on the vacuum pump control and vents the specimen chamber. After pressure equalization, she can open the cover plate of the specimen chamber. Together with the cover plate, the stage pans forward. Now different specimens can easily be placed on the round stage. The filament of an old used light bulb, part of a welded tube on a sample holder, a small cobalt plate, and a golden piece of jewelry. All specimens are assembled and we are ready to start. The material tester carefully closes the cover plate and switches on the two-stage high vacuum pump as well as the electronic control. It takes about 3 minutes to obtain a sufficient vacuum in the specimen chamber and column. Meanwhile, she turns on the monitor, initializes the motorized stage and boots the microscope control. Only now she is allowed to switch on the high voltage and the thermionic cathode. For the first time, a reasonable image appears on the monitor. It shows part of the specimen stage. Using the trackball, she moves the stage within the microscope. She looks for the place where the first sample is positioned, the used filament. The magnification is gradually increased. The position readjusted, and the magnification increased again. Now a plastic and high contrast image of the filament can be seen on the monitor. Originally, the coiled coil filament was quite smooth on the surface. Caused by the everyday use of the filament, new crystals have been formed. Tungsten atoms have evaporated and the outer regions of the filament have become polygonal. But how is this plastic image generated, and how does the microscope actually function internally? The animation first shows the schematic structure from the outside. The upper part is the so-called column. It is used to generate an electron beam. The lower part consists of the specimen chamber with cover plate. In the longitudinal section, the flange leading to the high vacuum pump is visible at the bottom. Thereby, high vacuum is generated inside the whole microscope. The round specimen stage may not only be moved to the left and to the right, but likewise in all other directions. It may also be tilted and rotated. All samples to be investigated are placed on the specimen stage. To create an electron beam, a V-shaped thin tungsten wire is used, the so-called thermionic cathode. Heated up by electric current, it emits electrons into the vacuum, indicated by small dots. Below the cathode, a metallic disc with a central borehole is installed, the anode. The anode is connected with a positive pole of a high-voltage source, the thermionic cathode with a negative pole. Further necessary components have been omitted for the sake of simplicity. The strong electric field between cathode and anode accelerates the electrons downwards. These electrons are called primary electrons. They form a broad, diverging beam which hits the specimens and the stage. But this way, the beam of primary electrons is not useful yet. An electromagnetic lens focuses it finely on the specimen surface. At the point of incidence, primary electrons knock out electrons of the sample material. These knocked out electrons are called secondary electrons. Additional components are necessary: electromagnetic deflection, raster scan generator, secondary electron detector, abbreviated as SE detector, and computer with monitor. The basic principle of the scanning electron microscope is to detect the secondary electrons and use them to build up an image. To increase the number of detected electrons, a positively biased grid is placed in front of the detector. The grid attracts the secondary electrons and leads them to the SE detector. And this is the way to generate a magnified image of the sample. The raster scan generator directs the electron beam to the left rear part of the sample and stops there for a short time. The number of secondary electrons is recorded in the SE detector. The signal is amplified and displayed as a dot at the top left-hand corner of the monitor. The electron beam pans slightly to the right, stops again. The measurement is repeated. In the same way, the next points on the sample are dealt with. The principle is, many recorded secondary electrons lead to a bright image point, few electrons lead to a gray image point, and none at all to a black one. An entire row is covered in this way. Then a second row, until finally a rectangular area has been scanned and an image appears on the monitor. If not only a few but many image points are used in the raster scan, a natural-looking image of the specimen surface can be seen on the monitor. Back in reality, the material tester selects low magnification again and looks for the second sample. It is an austenitic stainless steel tube with a longitudinal weld. Invisible to the naked eye, the scanning electron microscope reveals fantastic crystals. They have grown near the surface during solidification of the weld deposit. In some crystal directions, the solidification rate is particularly high and so-called dendrites form. Dendrites are crystals with many branches and tree-like shape. On the surface of the weld, they could grow almost freely without much disturbance and can now be observed well. Last in line is the golden piece of jewelry with a gemstone. The material tester is especially interested in the chemical composition of the gold material. Does the promised gold content really exist? Which other elements have been added? She chooses a place near the edge of the piece and selects a suitable magnification. Now she makes use of a fantastic method, the non-destructive chemical analysis with the scanning electron microscope. And it works like this. When the fast electrons of the electron beam, the primary electrons, reach the surface, they knock out electrons of the specimen material. These are the secondary electrons used for image formation. What happens in detail shows a schematically drawn atom from near the surface. Just like any other atom, it consists of a positively charged nucleus and negatively charged electrons. The electrons stay in energetically well-defined shells around the nucleus. A primary electron comes from above and accidentally knocks out an electron from the K shell of the sample atom. A vacant place remains as indicated by the yellow circle. This state is unstable. An electron from the L shell fills the gap and the energy difference is released in the form of a characteristic X-ray photon. This X-ray photon is called characteristic because its energy is quite characteristic or typical for the particular element. Now another transition follows. And finally the atom repairs itself with an electron from the vicinity, a free electron. So X-ray radiation is generated during the operation of the scanning electron microscope, namely X radiation, which is characteristic for the chemical elements present in the sample. If the energy and the intensity of the radiation are measured with an X-ray detector, then the chemical composition of the sample can be determined. The spectrum of the piece of jewelry builds up. Chemical analysis is then carried out using sophisticated methods with the help of a computer. Certain limitations must indeed be minded, but it's definitely a fine method, and above all, it is completely non-destructive, and even very small spots on a sample can be analyzed. And what has happened to the small cobalt plate, which was one of the samples? It was used to calibrate the measurement. This means to adjust it finely. The chemical analysis is finished now. Our piece of jewelry is genuine. The gold content amounts to about 70%. The balance is silver and copper.